So proposition 3.6, it says that, well, what I just told you, the differential is linear, but it also says that there is a rule for if we have a composite of two smooth functions, right? So I'll start with B. So like B, it says if you have the differential of, say, big G composed with big F, all right, at the point P, well, that's equal to the differential of big G at F of P, all right, composed with dF of P, where that's a mapping from, the tangent space at P of M all the way over to the tangent space of G composed with F of P at P, because apparently we're talking about F as a mapping from M to N and G as a mapping from N to P, I believe, big P. And so the little p, not to be confused with the big P, let me give it a foot. There you go. Okay. What else can I tell you about the differential? The differential of the identity map on the manifold at the point P is, guess what? The identity on the tangent space at P to M. That's pretty cool. And D, if you got yourself a diffeomorphism, then the differential at P from the tangent space at P of M to the tangent space F of P at M is an isomorphism. And there's more. The differential of F at P, the inverse of that, guess what? That is equal to the differential of the inverse at F of P. So these things are nice to know. Thank you for proving them in your homework. Oh man, I should have just not even written that down, because you're going to have to write it down for your homework anyway. Wasting precious time. All right, let's see what I can say here. So, proposition 3.8. So I told you guys I read chapter 3 in Jeffrey Lee's book, right? And so there, he takes a very, very different approach to discussing this, because he at the start of it just talks about all the different formulations of the tangent space and why they're equivalent. Whereas this book is much more kind to us in that it says, it spends a second on the geometric when, quickly transitions to the derivations, and then just stays there and talks about everything we can talk about for derivations. Then at the end of John Lee's chapter, he talks about different viewpoints. But one of the things that's fussy is that there is this local global issue in terms of, we've been looking at smooth functions on the whole of the manifold. But do you always want to be looking at smooth functions on the whole of the manifold? Maybe not, right? And it turns out that it's enough to, if you define a derivation at a point on functions which are only defined close to the point, it gets you all of the same data as if you define functions on the whole of the manifold. Because you can always take functions local to the point, and you can extend them using that bump function stuff to a function which is defined on the whole manifold in a smooth sense. So this, anyway, proposition 3.8 is part of that story. Proposition 3.8 says if M is a smooth manifold with a without boundary, and P is an element of M, and V is in the tangent space at P to M. All right, so if F and G are smooth functions on M, agree on some neighborhood of P, all right, then VF equals to VG. So it doesn't matter what happens like away from the point, the derivation, you know, like the value that the derivation takes on these two functions is completely governed by what they do near the point, which is intuitively obvious, right? But the proof is kind of interesting, right? He says, basically, the proof, I think I should write the proof down actually, because it's interesting. I'm probably going to regret doing it. It's okay. I'll get over it. H is F minus G, all right? So that's a smooth function that vanishes in a neighborhood of P, right? So that basically you've got H of Q equals to 0 for Q near P, right? Quote unquote near P, in some neighborhood of P, right? That's the case. And so what he says, he's like, okay, so let psi be a smooth bump function. C infinity M, smooth bump function. All right? That's identically equal to 1 on the support of H. Right, so psi of Q is identically equal to 1 for all Q in M such that what? H of Q not equal to 0, basically, right? The support of H is all the points where it's all the points where H is non-zero. It's the closure of the set of points where H takes non-zero values, right? And then what? He says because psi is identically equal to 1 where H is non-zero, the product of psi H is equal to what? Search your heart. It's equal to H. Okay. So then what? Well, since H of P equals to psi of P equals to 0, what's that tell us from the lemma that you guys are going to prove, right? Which is a close cousin to the one I proved carefully today. We've got that V of H is equal to V of psi H, which is equal to 0, right? And then that implies that VF equals to VG, all right. So, I mean, there's the proof. So the proof that the value of a derivation is completely governed by the values of functions near the point, it's intimately connected to the existence of these bump functions, all right? It turns out these smooth bump functions don't exist on manifolds that are not of the smooth type. If you look at an analytic manifold, in other words, a manifold where the transition functions are just analytic, or a complex manifold. Anyway, so a function where the transition functions are just assumed to be analytic, not necessarily smooth, then you don't have the bump functions, and you have to use other things. All right, you have to use something called the germ viewpoint. The germ viewpoint, instead of looking at functions, it looks at equivalence classes of functions which agree near the point. It's a little bit more abstract. It's described in here. Anyway, so a little bit short on time here, so let me just tell you proposition 3.9. What it tells us is that if we look at the inclusion map, my hated Yoda, from U to M, so let U be an open subset of the manifold, then the differential of the iota map, a mapping from the tangent space at P to U, all right, to the tangent space to P at M, is isomorphism. And let me just get to the point here, because you can talk a long time about this, but it's really simple. All we're saying here is the following: is that we identify the tangent space at P to an open subset of the manifold with the tangent space at P to the entirety of the manifold. All right. So, and this identification, he says, just amounts to the observation that basically this thing, d iota p of v, is same as v. The difference just being that, v would be thought of as acting on functions of smooth functions from u, right? So that would act on like c infinity u, whereas this guy would act on c infinity m, right? But you can see from the proposition that that's kind of the same thing, right? Whether or not the function's defined just on the open set, or if the smooth function is defined on the totality of the manifold, the way it behaves for the derivation just is governed by what happens close to the point. So what does it matter if the point is part of a manifold or if it's part of an open set inside the manifold? Either way, it should be the same. That is nevertheless proved in gory detail on page 56. And interestingly, this, oh man, son of a gun. So proposition 3.10 says that if M is n-dimensional smooth manifold, then for each P in M, the tangent space at P to M is an n-dimensional vector space. Let me just try to walk us through the proof really quickly. So the deal here is you got M, right? Here's a point P. So there's some chart domain around that U, right? And so there's a chart phi which takes you down to what? Phi of U. Okay? Now, I was confused at the end of last class. I was trying to argue that U has to be diffeomorphic to M. That's utter hogwash. Phi has to be diffeomorphic to phi of U. This is problem 1 in mission 2 for you guys.
U is diffeomorphic.
U is diffeomorphic to this image under phi. That's true. It can't be diffeomorphic to all of M, because all of M could have non-trivial topology, and on the other hand, phi of U is supposed to be an open ball. All right, so anyway. I shut up. Okay, so anyway. And he just calls this thing U hat. All right. That's a subset of Rn. He says it follows from proposition 3.6d, which I think is one of the things you guys are going to prove. What's 3.6d? Oh, so that says that so from 3.6d, which is one of the things you guys are going to prove, that, so think about this. D phi p is going from where? This is going from the tangent space at P to U to where? The tangent space at phi of P to U hat, right? But we know that those are isomorphic. Okay? But from this proposition, we know that the tangent space at P to M is isomorphic to the tangent space at P to U. So we've got an isomorphism from tangent space at P at M to tangent space at P at U, isomorphic to the tangent space at P at here, U hat. And then there is yet another theorem which says that this is isomorphic to the tangent space at P to Rn, rather phi of P of Rn. And that would just be by, I think, just the inclusion map of U hat into Rn. Okay? So I think it's actually this proposition 3.9 just applied to the context of U hat being an open submanifold of Rn itself. So therefore, we have the tangent space at P is isomorphic to the tangent space phi of P of Rn, right? But we proved earlier today that that has dimension n. That was the big thing we proved today, because that's a set of derivations of phi of P. Not obvious, it was Taylor's theorem, it was a mess, but we proved, so there you go. That proves that a smooth manifold has to have a tangent space of dimension m at each point. So I guess that's a good enough place to stop. I had so many more things to tell you today, but it's okay. There's another class next time. But anyway.